The purpose of this short video is to demonstrate a phenomenon known as proportional only offset. To do this, we're going to use our desktop process consisting of a loop controller, a pulse width modulation power circuit board, and a motor generator set as our process. We're going to use the loop controller to control the speed of the motor. So to do this, first I'm going to start in manual mode, and I'm going to increase the output until we get the motor to spin manually. This is not an automatic, so I'm simply adjusting power to the motor by hand until we get some motion out of it. You can actually see it spinning right there. You'll see the tape that we're using for a coupling between the motor and the generator. I'm going to increase this until I get somewhere around 50% on my process variable scale. There we go. I can display my process variable, 46%. So we're somewhere around 50% here, pretty close to 50. And we are in manual mode. Because the controller has set point tracking, it forces set point to be equal to the process variable. At this point, I'm going to throw the controller into automatic mode. When I go into automatic mode, now the controller will make adjustments to the output signal. That is, to make adjustments to the amount of power sent to the motor according to what it sees for the error, the difference between process variable and set point. Right now there is zero error. The process variable and set point are equal to each other, and the output signal here has been established by my former adjustments in manual mode. So right now there is zero error, or we would say zero offset between process variable and set point. This controller has been configured for proportional only control with a gain of 1. I can demonstrate that right here. Pressing the tune button, we have a gain of 1. So going back to our display here, I'm going to take the set point and adjust it for a higher motor speed. As I do this, you can see and hear the motor achieve a greater speed. It's spinning faster now. You can tell that audibly by the tone. But notice here on the process variable display, you notice the process variable no longer equals the set point. We have an error that's developed, and this is also known as offset. If you have pure proportional control, you will always end up with an offset like this at certain points throughout the controlled range. I'll show you towards the bottom end of the range. I'll decrease the set point. We'll see the offset go away. Process variable and set point are becoming more and more equal to each other. But if I keep lowering the set point, we see the same phenomenon at the lower end. Notice with my decreased set point, my process variable is not able to fully achieve the new set point value. I'm left with an error or an offset that persists, and I will always have this when I'm dealing with proportional only control. The reason for this is how proportional control works. It works by changing the output based on how much error we have. In other words, the only way a proportional only controller can actually achieve a new output value is if an error develops between the process variable and the set point. So long as process variable and set point are equal to each other, the output will remain fixed. So when you're dealing with a self-regulating process, as this is, which means in order to achieve a new process variable value, we need a new output value to send a different amount of power to the motor, you're always going to end up with offset. As I increase set point and call for a higher motor speed, that of course demands more power being sent to the motor to overcome the friction and drive it at a higher speed. However, if the process variable, that is the motor speed, ever were to achieve this new set point, the output would go right back to its former value, which we know would not be enough power to continue driving the motor at the new higher speed. Therefore, a proportional only control algorithm can never achieve the new set point value. It can only achieve the old set point value where it started. Any new set point value, whether higher or lower than original, would demand a different output in order to make this process achieve that new set point, and proportional only control cannot do this. So what we're left with is a bit of a conundrum. We have a control algorithm that works marginally well, but it leaves us with an offset we just can't get rid of. And the amount of offset changes with the amount of gain. I'll demonstrate here. Let's say we go back to this condition where we're roughly at 50%, approximately zero offset. I will hit the tune button once and I will change my gain. I'll lower the gain to approximately 1/2. So instead of a gain of 1, I'll now have a gain of about 1/2, and I'll store that. Get out of this, and now I can adjust the set point again. Pay close attention to the bar graphs. As I adjust the set point up, We're dealing with a system that does not have as much gain as it did before. Therefore, the change in output will not be as aggressive as it was before for a given amount of error. This means that it has an even harder time achieving a new set point value. I have a much larger offset here than I did before. This also holds true in the lower end. If I decrease my set point down, 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 calling for a lower motor speed, as I get down towards the low end of the scale, I see a much greater offset between PV and set point than I did before with a gain of 1. So decreasing the gain of a controller makes this proportional only offset phenomenon worse. Conversely, I can go to my tuning parameter, I can increase my gain. Let's say we go up to 1.7. I can store that and try a new set point value. Now I try a new set point value here, a higher value, and notice we don't have quite as much offset as before, but now we have an unstable loop. So this is the problem with going too much gain. In theory, more gain means less offset, but here's what happens in practice. More gain means the loop tends to be unstable. With a gain of 1.7 here, I might not even be able to get good control at the bottom. We'll see. Yeah, we still have a little bit of oscillation at the bottom. Not as much offset as before, owing to the greater amount of gain. It doesn't require as much offset or error to generate a new output value. However, the price I pay for that reduced offset is loop instability. So here is the problem we have with proportional only control. Too little gain, lots of offset. Too much gain, oscillation. So we try to strike a balance between those two bad effects and get something that's marginally useful or marginally practical for our loop control. The ideal solution to this, though, is to introduce a brand new element to our algorithm of control, and that's called integral action. That's the letter I in PID. PID standing for proportional integral derivative. Proportional by itself has limitations. Integral helps us overcome that limitation of offset.